Part 1. Right now, at a distance of roughly 130 million miles from Earth, something extraordinary is unfolding. Through the silent dark of space, an object the size of Manhattan moves with unfathomable speed, 210,000 kilometers per hour, cutting through the void like a silver ember flung from the hand of creation itself. Astronomers have named it Three-Eye Atlas. To the untrained eye, it may appear as just another comet, a frozen traveler catching the faint glimmer of the sun. But that illusion fades the moment you look closer. This is not a typical visitor. It is the third confirmed interstellar object ever recorded, and every new piece of data we gather about it seems to bend our understanding of how comets behave and perhaps of what the universe allows. For centuries, humanity has looked upward and asked what lies beyond our solar system, imagining the stars as distant suns surrounded by worlds we might never reach. But now, in the quiet patience of 21st century astronomy, fragments from those distant realms have begun to find their way to us. They are travelers, wandering debris cast out by the violent birth of other solar systems, drifting for billions of years through the cold interstellar gulf until gravity from our own star draws them in for a brief, radiant encounter. In 2017, it was Oumuamua, a shard that passed swiftly and silently. 2 years later, Borisov followed, more familiar, more comet-like. And now, Three-Eye Atlas, an object whose presence seems almost deliberate, almost aware. This is where our story begins. When astronomers at the Asteroid Terrestrial Impact Last Alert System, ATLAS, first detected it on July 1st, 2025, they immediately noted something odd. Its path was not closed, not an ellipse that would bring it back around the sun. It was hyperbolic, a single graceful curve of escape. That meant only one thing. It came from beyond. An interstellar traveler. That alone would have been enough to secure it a place in scientific history. But then came the details, the strange glow, the metallic vapors, the behavior that refused to match any model we had. The initial observations suggested an object of between 2 and 6 kilometers in diameter. Yet it was unusually bright for its size, surrounded by a shimmering halo of vaporized carbon dioxide far richer than water, as though it were a frozen fragment from a world unimaginably cold. And then came something even stranger. Spectrographs began to detect a whisper of nickel gas. Nickel, not iron, though those two metals are almost always found together in the cosmos. That absence was as significant as any presence. It hinted at chemistry unknown, or perhaps at processes that we have never before seen unfold in nature. And as telescopes across the world turned their gaze toward it, something else caught the attention of observers. The object was releasing luminous metallic vapor, yes, but doing so with eerie precision. Its emissions pulsed, not randomly, but rhythmically, like a pattern repeating across days. Comets, by their very nature, are chaotic. They tumble, they sputter. Their jets shift as they rotate, causing slight changes in their orbits. But Three-Eye Atlas did not waver. Its course remained exact, unbent, unaltered. Even as it approached the inner solar system, where the gravitational influences of the planets grow complex, it held to its projected path with mechanical fidelity. To many astronomers, that precision was merely curious, an anomaly to be studied. To others, it stirred something more primal, a feeling that perhaps, in this visitor, we were witnessing not merely physics but purpose. Could that be? Could an object from beyond the stars travel so far, so fast, and yet move as if following a script? Or were we simply being confronted with the limits of our understanding? In the days that followed its discovery, the world's observatories coordinated an unprecedented campaign of observation. The Very Large Telescope in Chile, the Gemini South Array, NASA's own infrared facilities, all turned their instruments toward this newcomer. The data began to pour in, a flood of measurements and spectra, each revealing a little more of the mystery and deepening it at the same time. By mid-August, the first reports confirmed what many had suspected. The comet was unusually active even while still far from the Sun. Typically, such bodies awaken only when solar heat begins to vaporize their icy surfaces, usually within 2 astronomical units of our star. But 3I Atlas began venting gases nearly 4 units out, a distance where temperatures linger around minus 200 degrees Celsius, far too cold for water ice to sublimate. Yet there it was, shedding a tail of light across the void, like a beacon proclaiming its presence. Then came the encounter with Mars. On October 15th, the object swept past the red planet at a distance of barely 12 miles, a passage so close that it defied coincidence. The Mars Reconnaissance Orbiter's high-resolution camera, HIRIS, captured images at that moment, and though the photographs have not yet been publicly released, those who have glimpsed them speak in cautious tones. They say the surface features do not resemble the rugged, irregular terrain typical of icy bodies. Some even hint at symmetry, subtle, geometric striations across the nucleus, patterns that seem almost designed. And then, 12 days later, came the storm. On October 27th, the Sun unleashed one of the most violent coronal mass ejections of this entire solar cycle. A surge of plasma, billions of tons of charged particles, blasted outward at millions of kilometers per hour, an eruption so powerful that, had it been directed toward Earth, it might have caused widespread electrical blackouts. Instead, it was aimed directly at 3I Atlas. Astronomers braced for what seemed inevitable. Comets are fragile. Even modest solar outbursts can tear them apart. But when the storm struck, the unexpected happened. 3I Atlas held steady. No fragmentation, no deviation, not even a measurable wobble. It absorbed the full force of the solar tempest and continued along its trajectory as if nothing had happened. The Russian Space Research Institute released preliminary data confirming that the object's orbit remained entirely unchanged. Its signal faint, but steady. It had withstood energies on a scale equivalent to millions of nuclear detonations without the slightest alteration in speed or direction. How does a body of ice and dust, barely a few kilometers wide, survive that kind of onslaught? What materials could grant such resilience? Could its composition be fundamentally different from anything we've ever seen? Or are we, perhaps, misjudging what we're actually looking at? For now, we have only questions. But questions, as every scientist knows, are where discovery begins. Out there, in the silent gulf between worlds, a lone object drifts, luminous, metallic, steadfast, its tail streaming like a banner through the black. It has crossed the unimaginable emptiness between stars to find us, and with each passing day, it pulls us deeper into its mystery. Soon we will learn more. Soon the veil will lift. But not yet. Because before we can grasp what 3I Atlas truly is, we must first understand how it behaves when the forces of a living star bear down upon it. And that story, perhaps the most remarkable of all, is only just beginning. Part 2. When the solar storm struck 3I Atlas, it did more than test the integrity of a frozen wanderer from another star. It also tested the limits of our understanding. In the days that followed, as data from observatories across the world began to stream in, scientists realized they were witnessing a phenomenon that could rewrite what we know about how interstellar bodies interact with our Sun. The object's response, or rather its astonishing lack of one, was impossible to ignore. For any known comet, the violence of that coronal mass ejection should have been catastrophic. The blast would have stripped away its outer layers, fractured its nucleus, and sent debris scattering along its orbit. Yet 3I Atlas remained whole, its brightness unchanged, its trajectory unwavering. At the Russian Space Research Institute in Moscow, the team led by astrophysicist Ekaterina Solovyova spent sleepless nights analyzing telemetry from the solar observatories that had recorded the event. The readings were clear. The plasma wave impacted the comet directly. For a few brief hours, electromagnetic interference blanketed every instrument pointed in its direction, and then slowly the signal returned, faint but stable. Solovyova's team expected to find at least a minor alteration in the comet's orbital elements. They found none. Its perihelion distance, eccentricity, and inclination were all identical to pre-impact predictions, down to the 5th decimal place. To maintain such precision, the object would need to possess an internal structure orders of magnitude stronger than the loosely bound aggregates we have come to associate with comets. The data suggested a density far higher than expected. Traditional cometary nuclei are porous, more akin to snowdrifts than solid rock. 3I Atlas, however, appeared to absorb the storm's energy with stoic indifference. That raised the first major question: what is it made of? When the James Webb Space Telescope aimed its infrared spectrometers toward the object before the storm, the results were already peculiar. The ratio of carbon dioxide to water vapor in its coma was reversed, nearly 9-1. Water, normally the dominant volatile, was relegated to a minor role. Carbon dioxide and carbon monoxide ruled the spectrum, along with traces of formaldehyde, methanol, and hydrogen cyanide. But it was the metallic lines that drew gasps from those who first examined the readings. Nickel, ionized, radiant, unmistakable, and no iron to accompany it. Nickel vapor at a temperature of almost 3,000 degrees Celsius, streaming from a body that should be at minus 100 degrees, defied every thermodynamic model. 2 independent teams, one from the University of Cambridge and another from the Max Planck Institute for Astronomy, ran simulations to reproduce the observations. Both failed. Their models could not reconcile the measured temperature with the known energy input from sunlight. Something else was heating the nickel, some internal process, some mechanism unknown. Dr. Rohan Rahat Gonkar and Dr. Daryl Seligman, working jointly through the European Southern Observatory, proposed a daring hypothesis. They suggested that the nickel was bound within exotic organometallic compounds, molecules capable of releasing the metal when broken apart by ultraviolet radiation. It was elegant, mathematically consistent, and yet troubling. Such molecules have never been observed in space. For them to exist, they would require conditions so specific, pressures, radiation intensities, and chemical balances, that no known region in the galaxy could easily produce them. If they are right, then 3I Atlas may represent chemistry that predates the formation of our own solar system, remnants of a molecular cloud forged in the earliest epochs of the Milky Way. As these debates unfolded, new data poured in from ground-based observatories. The Very Large Telescope in Chile captured a continuous series of spectra over several nights, and the results deepened the mystery. The intensity of the nickel emission fluctuated with a rhythmic regularity every 11 hours, suggesting a rotation period almost precisely aligned with that cycle. The jets venting from the nucleus appeared to emerge in symmetrical pairs, switching positions like alternating beacons. This was not chaotic outgassing. It was ordered, patterned, predictable. The geometry of those jets produced momentary oscillations in the brightness curve, like a heartbeat echoing across millions of kilometers. At NASA's Goddard Space Flight Center, analysts began cross-referencing these brightness variations with radar data from the Goldstone Deep Space Communications Complex. The radar echoes, faint but decipherable, hinted at something astonishing. The nucleus of 3I Atlas was not irregular, but elongated and smooth, almost spindle-shaped, perhaps even faceted. Unlike most comets, whose surfaces are rough and uneven, this one seemed symmetrical. Its albedo, its reflective index, was unusually high, closer to that of metallic asteroids than of icy comets. Combined with the earlier detection of nickel vapor, this painted a portrait of a body far denser, stronger and more reflective than any we had encountered. Then came the data from Mars. The high-rise camera aboard the Mars Reconnaissance Orbiter had captured high-resolution images during the comet's breathtakingly close pass, just 12 miles above the Martian surface. Though those images remain under internal review, a few descriptive details emerged in scientific briefings. The surface, according to preliminary analysis, exhibited linear formations, bands, ridges, and what appeared to be polygonal divisions stretching across the nucleus. These were not random fractures. They formed a network of interlocking planes, their alignment too uniform to be the result of natural sublimation. Scientists compared them to the cooling cracks in basaltic lava, but the scale and precision did not fit. Whatever shaped those lines did so under conditions we have yet to identify. In the wake of these revelations, discussion among the world's astronomical community intensified. Some argued that 3I Atlas was simply an extraordinarily resilient comet, forged in the frozen periphery of another star system, its strange chemistry the product of unfamiliar elemental ratios. Others ventured further. Could the object be an artificial probe, perhaps long abandoned, now mistaken for a natural body? The notion seemed fanciful, but the data refused to rule it out completely. Even Avi Loeb, the Harvard astrophysicist who had previously suggested that Oumuamua might have been of artificial origin, urged caution. He proposed that if the object's trajectory continued to exhibit such remarkable stability, then at the very least we were observing a phenomenon of controlled dynamics, whether natural or otherwise. Still, science thrives not on speculation but on measurement, and the measurements continued. The James Webb Telescope revisited the comet after the solar impact, and what it found astonished even the most seasoned observers. The thermal signature had barely changed. Its surface temperature, once calculated at approximately -100 degrees Celsius, remained constant. If the coronal mass ejection had struck with the expected energy, the outer layers should have been vaporized. Yet there was no measurable increase in gas production, no surge in brightness. The comet's coma, instead of expanding, appeared to contract slightly, as if its atmosphere had momentarily compressed and then settled. In a rare joint statement, NASA, ESA, and Roscosmos confirmed that the object had endured one of the largest solar events of the decade entirely intact. They emphasized the importance of continued monitoring, particularly during its upcoming gravitational interactions with Jupiter and Venus. According to the latest orbital calculations, 3I Atlas's path would thread through the solar system with uncanny precision, skimming the giant planets at distances optimized for gravitational assists. To some, that looked like coincidence. To others, it looked like navigation. Meanwhile, laboratories on Earth began studying analog materials to replicate the comet's observed properties. Experiments with nickel-bearing ices under vacuum conditions failed to reproduce the luminous metallic vapor seen by telescopes. Even at artificially induced temperatures approaching those of molten metal, the spectral lines differed. The vapor from 3I Atlas displayed unique ionization ratios, specifically an overrepresentation of singly ionized nickel compared to doubly ionized forms. This indicated an excitation mechanism that was non-thermal, likely electromagnetic in nature. But where could such fields originate? The object's size and velocity left little room for internal magnetism of that strength, unless, as some suggested, it carried remnant magnetization from its birth environment. Perhaps a region around a magnetically active star whose field had imprinted the nucleus during its formation. Whatever the explanation, the implications were profound. For planetary scientists, this meant that interstellar objects might preserve signatures of their native stars' magnetic topographies, encoded within their crystalline matrices. Studying them could reveal information about stellar environments light years away, a kind of cosmic geology stretching across the galaxy. 3I Atlas had become not merely an anomaly, but a messenger, bearing within its substance the physical memory of another sun. The intensity of global observation reached a fever pitch by mid-November. Amateur astronomers joined professional observatories in the International Asteroid Warning Network's Comet campaign, using instruments from backyard telescopes to the Great Keck Observatory in Hawaii. They tracked its motion night after night, submitting positional data to a shared database. The collective effort achieved an unprecedented feat, the most precise trajectory mapping of any interstellar object in history. The margin of error in its predicted coordinates shrank to less than 1/10,000th of an arcsecond. In practical terms, that meant that if the comet's course were projected onto the surface of Earth, we could pinpoint its position to within a single meter. That precision yielded another surprise. The tiny deviations expected from jets of gas pushing against the comet's surface, the so-called non-gravitational accelerations, were absent. It moved as though it were immune to the subtle thrusts of its own outgassing. This reinforced the idea that the jets themselves were symmetrical, cancelling each other's momentum perfectly. To maintain such equilibrium, naturally, would require either extraordinary coincidence or a shape so precisely balanced that every reaction was countered by an equal opposite. A natural sculpture of balance carved by billions of years of cosmic travel, or a construct, a design. At the Institute for Planetary Science in Arizona, Dr. Helen Morita led a team using computational fluid dynamics to model the jets observed by the VLT. Their simulations produced plumes that rotated with the object's spin, creating alternating bands of light and shadow around the nucleus. When compared to telescope imagery, the match was nearly perfect, confirming the 11-hour rotation period. But it also revealed something subtle. The pattern of gas release shifted slightly each cycle, by a fraction of a degree, as if compensating for changes in solar illumination. That behavior could be explained if volatile pockets beneath the surface were opening and closing in a feedback loop, responding dynamically to heating. Yet the precision of the timing raised eyebrows. It was as if the comet knew how to balance itself. Even more perplexing were the changes in polarization detected by the Nordic Optical Telescope in September. The light scattering from the coma displayed periodic alignment, oscillating between orientations consistent with crystalline dust rather than amorphous ice. This suggested that the ejected particles were structured, perhaps even plate-like, tiny reflective surfaces glinting as they spun. Such features could naturally arise from layered ice, but they could also resemble reflective panels, thin and metallic. For weeks, the data fueled debates in conferences and papers. Some researchers invoked microcrystalline graphite or silicate mirrors as explanations. Others dismissed the idea entirely. Meanwhile, the comet's trajectory brought it steadily inward, toward its closest approach to the Sun. Each day, as it drew nearer, astronomers expected to see a surge in brightness, a classic hallmark of sublimation accelerating under solar heat. Yet 3i Atlas defied this, maintaining a consistent luminosity, neither dimming nor flaring. It was as if it had reached a thermal equilibrium, immune to further heating. When it finally rounded the Sun, emerging on the far side, its appearance remained unchanged. No new jets, no new fragments, no loss of structure. The object behaved not as a fragile conglomerate of ice, but as a solid body engineered to endure extremes. As the comet drifted outward again, passing through the plane of the ecliptic, observatories noted another peculiar feature, a secondary tail forming briefly in the direction opposite the expected one. This anti-tail phenomenon, previously seen in rare cases, typically results from perspective effects when Earth crosses a comet's orbital plane. But this time, the anti-tail evolved independently of our viewing geometry. It appeared, brightened, rotated, and merged back into the primary tail within days. Some astronomers speculated that electromagnetic interactions between the comet and the solar wind could be shaping the dust in unexpected ways. Others wondered if internal magnetic fields were influencing the motion of charged particles around the nucleus. By late November, as the International Asteroid Warning Network intensified its tracking, 3I Atlas became the benchmark for planetary defense exercises. Its extreme stability provided an ideal target for testing long-range orbital prediction algorithms. For the first time, researchers were able to refine tracking techniques that could one day determine whether a future object, perhaps one on a collision course with Earth, could be diverted in time. Ironically, the mysterious visitor that had arrived unannounced from the stars was now helping us prepare for the day when such an encounter might threaten our planet. And yet, beneath all the data and discipline, there lingered an undercurrent of unease. Every instrument pointed at 3I Atlas seemed to whisper the same quiet contradiction. It looked like a comet. It acted like something else. The absence of spin drift after the solar impact, the perfect symmetry of its jets, the impossible strength of its structure, and the unearthly glow of its metallic emissions, all of it painted a picture that science struggled to fit into known categories. At a symposium held in Geneva, astrophysicist Thomas Keller summarized the mood succinctly. "We are forced," he said, "to confront two possibilities. Either this object represents a class of interstellar body so radically different from anything we have encountered that it will require a redefinition of cometary physics, or it is not a comet at all." The room fell silent after that. Not because the audience believed in hidden intent, but because they could no longer dismiss the scale of the unknown before them. As weeks passed, the comet continued its silent course, a steadfast thread of light weaving through the inner solar system. It was visible even to modest telescopes, an emerald-tinged point trailing a faint, silvery plume. But behind that tranquil image lay numbers that did not add up, forces that did not behave, chemistry that did not belong. And so, the question that began as a whisper in July had become an echo reverberating across every observatory on Earth. What exactly is 3I Atlas? Was it a relic of creation, a fragment of some primordial world forged in the icy edge of another star's domain? Was it a messenger from a civilization beyond, its voyage measured not in years but in eons? Or was it simply a cosmic anomaly, proof that nature, in its endless creativity, can still astonish us when we believe we have understood her laws? Whatever the answer, one truth had become undeniable. The universe had once again reminded us that it is larger, stranger, and more alive with mystery than our equations can yet contain. And as 3I Atlas glided past Jupiter's orbit, reflecting the cold sunlight of our distant star, humanity stood watching, awed, humbled, and waiting for the next revelation. Part 3. To understand the meaning of 3I Atlas, we must look not just at its strange chemistry or impossible endurance, but at the legacy of human curiosity that made us able to see it at all. For centuries, comets were omens, celestial ghosts drifting through superstition. They inspired fear long before they inspired science. Only in the past few hundred years did we learn to see them as natural phenomena, fragments of the ancient past, remnants of planetary formation. They became symbols of wonder rather than dread. But now, as 3I Atlas crosses our sky, it reminds us that the line between wonder and fear, between mystery and revelation, is as thin as ever. Every great leap in our understanding of the cosmos begins the same way, with an anomaly. In the 17th century, Tycho Brahe charted the motion of a comet across the heavens, and proved that it lay far beyond the moon, shattering the old idea that the heavens were unchanging. In the 20th, Halley's comet returned as predicted, validating Newton's universal law of gravitation. And in the 21st, we have witnessed something even greater, a visitor not of our solar system, but of another, a fragment of another sun's creation, drifting across the gulf of interstellar space. Each one of these milestones has forced us to see the universe anew, to redraw the maps of our understanding. 3i Atlas is no different, though it carries with it a weight that none before have borne. It is not merely an object to be measured, it is a messenger, an emissary, from a realm we cannot yet reach. The instruments that captured its light, the James Webb Space Telescope, the Very Large Telescope, the Mars Reconnaissance Orbiter, are themselves marvels of human ingenuity. They represent generations of engineers, scientists, and dreamers who dedicated their lives to looking beyond the limits of our world. Without them, this story would have passed unseen, a silent arc of light lost in the infinite dark. Consider for a moment the journey that brought us here. In the deserts of Chile, under skies so clear that the Milky Way casts shadows, the European Southern Observatory's telescopes turned toward a faint moving speck. Behind each of those instruments are hundreds of minds, mathematicians who calculate orbits, technicians who maintain precision optics, programmers who build the algorithms that capture a passing flash of light and convert it into numbers. In Pasadena, analysts at NASA pored over infrared spectra, line by line, searching for patterns invisible to the human eye. Across the Atlantic, teams at the Max Planck Institute reconstructed the comet's shape through radar echoes bouncing off its surface. Each of these fragments of human effort came together like the pieces of a cosmic puzzle, forming a portrait of something both alien and familiar, a relic of physics, chemistry, and chance. And yet, behind every equation and observation, there is something deeper, a quiet sense of awe. Astronomers who have devoted their entire careers to studying distant bodies often describe a moment of stillness when the data gives way to meaning, when the numbers become something alive in the mind. They speak of it as a kind of reverence, a connection to the vastness that humbles and inspires. It is this same reverence that now surrounds 3i Atlas. No matter what its true nature proves to be, it has reminded us that discovery is not only about answers, but about the questions that endure. As the comet moves away from the sun, it carries with it the invisible fingerprints of our star, the charged particles from the solar wind now embedded in its frozen shell. It will carry traces of our system into the dark, just as it brought traces of another system here. In this way, it becomes a vessel of exchange, a courier of cosmic history. It reminds us that the universe is not a series of isolated systems, but a web of connections where matter and energy travel endlessly, binding stars together across unimaginable distances. When the first interstellar object, Oumuamua, was discovered in 2017, it was a fleeting whisper, an enigma that passed too quickly for us to study in detail. 2 years later, Borisov gave us our first clear glimpse of what an interstellar comet could look like, confirming that the galaxy is alive with such wanderers. Now, with 3i Atlas, we have entered a new era, an era not only of detection, but of comprehension. We are beginning to decode the language of interstellar matter, to read the frozen stories of other worlds. If we step back, we see how each discovery has prepared us for this one. The Veracy-Rubin Observatory, soon to come online, will scan the night sky with such sensitivity that it will detect thousands of new moving objects every week, some of them almost certainly interstellar. Missions are already being proposed to intercept them, to launch spacecraft pre-positioned near Earth's orbit that could race out to meet these travelers, photograph them, even sample their dust. For the first time, we stand on the threshold of capturing material that was born around another star and bringing it home for study. The prospect is staggering. Within our lifetimes, we may hold in our hands the ancient building blocks of another solar system, the seeds of another world. But there is another side to this revelation, one that touches something almost philosophical. 3i Atlas challenges not only our science but our sense of place. For so long, We have imagined ourselves as dwellers of a single solar system, bound by the gravity of one star. Now, we begin to see that we are participants in a larger network, a galactic ecology of drifting fragments and shared histories. Our solar system is not an island. It is part of a greater current, a river of matter that flows between stars. Every comet, every interstellar rock that passes near us is a trace of that river, a message written in frozen gas and dust. Perhaps that is the truest meaning of this discovery, not that 3i Atlas might be artificial or mysterious, but that it connects us in a tangible way to the rest of the galaxy. We have long looked at the stars and wondered what lies there. Now we know that pieces of those distant worlds come to us. They arrive unbidden, carrying within them the echoes of their origins. They tell us that the same physics, the same chemistry, the same elemental forces that shaped Earth are at work across the cosmos. The object's resilience in the face of the solar storm remains one of the great unsolved mysteries of this era. Some researchers propose that its internal structure may be crystalline rather than amorphous, a lattice of ices and metals fused together over billions of years of exposure to cosmic radiation. Others suggest that the material may have undergone natural sintering during its passage through interstellar space, compacting into something harder than rock. Whatever the explanation, its strength is undeniable. It endured a blast that could have disintegrated any known comet and emerged unbroken. That resilience will inform future studies of planetary defense, of material science, even of how we design spacecraft to withstand radiation and impact. In time, as it drifts farther from the Sun, 3i Atlas will fade from view. By the middle of 2026, it will have passed beyond Jupiter's orbit. By 2027, it will cross into the realm of the outer planets, its tail dimming until even the most powerful telescopes can no longer see it. After that, it will vanish into interstellar darkness once more. But the data it leaves behind will endure for generations. Spectra, light curves, orbital solutions, and a million images capturing its brief visit. These will become part of the shared archive of human knowledge, preserved in databases and observatories across the world. Decades from now, new scientists will return to that data with better tools, sharper minds, and new questions, and perhaps they will find in it something we missed. The story of 3i Atlas is, in the end, not just about the object itself, but about us. About the species that built instruments capable of detecting a speck of light 100 million miles away and recognizing in it the echo of another sun. It is about our hunger to know, our refusal to stop asking questions even when the answers elude us. In its cold, silent passage, this interstellar traveler has reminded us of something essential, that we are part of a universe still unfolding, still full of mysteries waiting to be discovered. When future generations look back on this time, they may not remember every statistic or every spectrum, but they will remember that we noticed. That when the darkness between the stars sent us a visitor, we turned our eyes upward and we listened. They will see in our response the telescopes trained, the scientists debating, the citizens tracking its path from their backyards, a reflection of humanity's oldest instinct, to understand the sky. And perhaps, centuries from now, another civilization around another star will detect a faint comet gliding into their system. They will observe its tail, analyze its light, and find traces of carbon dioxide, water, and nickel. They will wonder where it came from, what distant sun once warmed it, and who might have watched it pass. In that moment, they will be doing what we are doing now, searching for meaning in the shared language of the cosmos, and perhaps, unknowingly, they will be studying something born here, from our own solar system, carrying with it the fingerprint of our sun. 3i Atlas will travel on for billions of years, crossing gulfs we cannot imagine, its frozen surface marked by the faint signatures of our star's warmth. somewhere in the endless dark, it will remain as a record of this encounter. Proof that, for a brief moment in time, two systems touched across the void. This is the gift of the universe, that it allows us to witness such moments, to glimpse the vast network of connections that bind all matter and all time. And as we stand beneath our sky, watching a single moving point fade into the distance, we realize that we too are travelers, bound to a small world orbiting an ordinary sun, part of a grand story still being written. The mystery of Three-Eye Atlas will endure. Whether it is a relic of cosmic dawn or something still beyond our comprehension, it has already changed us. It has reminded us that science is not merely the pursuit of certainty, but the celebration of mystery. It has reminded us that the universe is not silent. It speaks if we learn how to listen. And as it drifts away, carrying our questions with it, we are left with a quiet truth, that in every fragment of ice and dust, in every glimmer of light across the dark, there is a reflection of ourselves, curious, searching, and forever reaching toward the stars.